How's it going? Today we're going to look at exponential and logarithmic models. Models is just a nice, easy word for applications. Yeah, everything we're doing today is applications. Now, in class, we started with this Starbucks data, little lab activity thing. And you weren't here. I'm going to kind of cruise through it, but it is important that you kind of at least follow along. You don't have to enter the data, but I referenced this Starbucks lab several times. So here we go. Right, so I started off and I got a bunch of data from how many Starbucks stores there were. So I started in year 1990 and then just went every 2 years looking at how many stores there were each time. And I have this. And we entered this in our calculator. It is worth mentioning that here that we never used the year. We chose 1990 to represent time 0. So we actually typed in 0, 2, 4, 6, 8, and so forth. Now, with that data, we set up a graph, we looked at it, and so here's what it looked like. It was gorgeous. I'm not going to lie. It was just like this perfect looking exponential graph. So we ran an exponential model on this, and this was the model that we ended up using. Now let's talk a little bit about what this model should mean to you. You should recognize that this was the initial number of stores at time 0. Now that's not exact, it's off a little bit, and recognize that this is just real life data, and real life data never works perfect. So, but this should be pretty close to your initial value. This is your growth rate. Remember the version where we had 1 plus R, and R was the percent increase? So this is growing at 36%. That's a pretty impressive growth. Good business plan by Starbucks. Then our goal was to kind of discuss the fit, and it did fit real nice. And then we used it to extrapolate. Extrapolate means that you're going to predict something beyond what the data shows. So we look towards the future from the data we had. So we did 2020. Remember that 1990 was year 0. So we did second trace value and put in 30, because this is really time 30. And 2030 would have been time 40, and we were testing to see how many stores there would be. So what we got at in 2020, there were 919,437 stores. And in 2030, it was it was 19,415,205. All right, so then I went and I Googled the same way I got the original data. I looked to check this 2020 data to see how accurate it was. And as nice as it started off, this was way, way, way off. And it should probably make sense that 19 million stores, really? I even Googled how many McDonald's there were, and we're nowhere close. And McDonald's is going to serve more people than Starbucks. Not everybody drinks coffee, but everybody likes a good quarter pounder. So something's wrong. That's what we decided. Something's wrong. This is not a very good representation. Even though it looked like it fit, it didn't really fit. So then I had them look at some other graphs. This kind of comes from the textbook that we're not really using, but we are using, which everything's based off this textbook. So I did this screenshot from our textbook and had them look and see if they could find a different graph that they felt might be a better representation. So take a minute. Do any of those look like they might work better for what we want? Well, exponential is what we did, and it did not work. But we wanted to sort of follow this path. So what we looked at was this logistic model. See how it increases exponentially, but then at some point it levels out. And that's what Starbucks was doing. It was, yes, it increased dramatically initially, but at some point, you're going to have to level off. You can't have everybody have their own Starbucks in their house, so this was a new graph for us, this logistic graph. So we're actually doing exponentials, logarithmic, and logistic graphs. So we did then run a regression, and you actually have this option in your calculator. When you go try to run a regression, if you scroll down just a little bit farther, you'll see logistic as one of the options. And it is a messy looking equation. And I'm going to go ahead and write it so you can see here's what it looked like. It actually takes your calculator a little bit to run it because it's a little bit intense to find all the data that works. So this is what the equation looks like when we ran the logistic on that data. And this is what a logistic model looks like. I mean, that's it. Now, we're going to talk a little bit about that and what all these numbers mean. But just kind of, and then we did the predictions, and they were much closer and a better representation of the data. So before we get into the other types of modeling, we're going to go ahead and focus on this logistic model. And so I have here this formula here, and it has several variables in it. You have your Y value, that would have been the number of stores, and then you have this X that would have been how many years. But look at everything else you have. You have this C value, you have an A. E is just our natural 2.718. So that's just a number. But then you also have this K value. So you actually have a CA and a K, all of those unknowns that when we run the regression, the calculator will find for us. These are all constants. And the one that sits there that is helpful is that C. C is called our limit to growth. So that tells us what this is leveling out at the top, because you're going to have two horizontal asymptotes. There's always an asymptote at 0, and then you have one at that C value up here that tells you what you're maxing out at. So let's start with an example where we actually know the logistic model. This is a model that represents the population of deer after T years in this state park. And so I have 3 questions for us. The first question is, what was the maximum number of deer possible? Well, hopefully you remembered what I just got done saying. It's the C value. It's up on top. So the maximum number is 1,001. That's all that the park can hold. My next question was, what is the initial number of deer? And it's going to be tempting to try to pick that number off of that formula, but the initial number is not just sitting there like it is in the exponential. Okay, so to find the initial number of deer, you have to make time equal 0. So we're going to put 0 in for T right here. Now, you can go to your calculator, but I'm going to tell you it's going to work way better if you do some mental math. Because really, if this is 0, what's 0 times this negative 0.2? And I should mention too, I know your notes are way tinier than this. You might make note that that's a 0.2 there. Some people miss that. But anyhow, so 0 times this, that's all 0. And what is e to the 0? 1. And what is 1 times 90? Plus 1. Okay, look at how easy it is to do all of that just in your head versus typing that mess in your calculator. So what you really end up with is 1001 divided by 91. And now I would go to my calculator to divide that out, and it looks like I'm going to have 11 deer initially. Okay, the last question then here is, when will the number of deer be 600? Okay, so what that means is I want the population to be 600. And I'm looking for the time. Now, when we first did this, we would have typed this all into Y1. We would have put 600 in for Y2, and we would have tried to see where they intersected. But now we know how to get this variable out of the exponent because we can use a logarithm to switch forms. But there's quite a bit of work to happen before that. Now, I don't know what I was thinking. I didn't give us near enough room to do this. So I'm going to have to squeeze it in. Bear with me. You're going to have to write little on your page also. Okay, so what I want to do is I want to put, so I'm going to kind of do, I don't know. I'm going to try to squeeze it in right in this space. So I'm going to put 600 in for the P of T. And it's going to equal my 1001 over 1 plus 90. I can't add those together because the 90 is getting multiplied by the e to the negative 0.2t. Okay, now I'm trying to isolate that t. So typically what we will do, since I can't actually evaluate any part of this, what I really want to do is get rid of this messy fraction. So I'm going to take this whole thing and I'm going to move it to this side. So it's going to be in front of the 600. Or I could put it after the 600. It doesn't really matter. I might put it after the 600. But it's that whole messy fraction right there. I'm sorry, it's not the whole messy fraction. It is just the messy denominator that I'm multiplying over to the other side. And then I'm going to immediately come back and I'm going to divide by the 600. I could try to distribute it, but it gets a little bit tricky, and then it's just going to make our numbers bigger. Let's make our numbers smaller. So then I'm going to divide by 600 on both sides. All right, so again, you're going to have to be careful that you are always using full values. You can write 2 decimals on your paper, but then you're always going back and using full values. My next thing I would do is I would subtract the 1. You just start peeling stuff away here. So subtracting the 1 is a 0.67, but I still got to do it in my calculator because I got to keep that number going. Then I'm going to divide by 90. And I got 0.007. And now I'm ready to switch to a logarithm. This is a base E. So I am so sorry. What a mess. I'm coming up here at the top so I don't run out of room again. So I'm going to change this to a natural log of 0.007 equals your exponent, negative 0.2t. And then the last step is going to be to divide by that negative 0.2. And then I'll have my t value. So in my calculator, I'm going to do my natural log of 0.007. Close your parenthesis on that, then divide by negative 0.2. And I end up with t equaling 24.81. Now that's my time measured in years. All right, now it is okay to have part of a year, so I'm going to go ahead and leave that. It didn't really tell me a starting year, so I'm just going to say 24.81 years. And that's when the population will reach 600. Okay, so you're still just doing a logarithm. You just got some grunt work to work through before you get to that stage. All right, and then we're going to try going the other direction. Could you write a logistic model? So I have all the info. Now I'm going to figure out what that A and that K and that C value are. Now remember, one of them sits there, but the others we're going to have to work for. So I kind of think of this as a 3-part stage. Now, which one of those do you think, A, C, or K? I guess I should start here. The initial value is 5, the limit to growth is 15, and it passes through this point 110. So which of those are we using first? All right, we are using the limit to growth. This limit to growth is the C value. That's the easy one. So this is step 1. C is going to equal 15. There's not really any work, but I'm going to make a note that that's the first thing that I do. I figure out what C is. Okay, now the next thing I'm going to do, I'm going to work on that initial value. Now remember, the initial value does not just sit there, but you kind of work through it. The initial value is supposed to be 5, and that happens at time 0. So think of this as an ordered pair 0, 5. So that's what I'm going to do for step 2. I'm going to put in 0, 5. So 5 is equal to, I know that my initial value is, that my limit to growth is 15. 1 plus, I don't know what A is, but this is E to the negative K times 0. Okay, that times 0 is going to help because look at what's going to happen here. This is going to be just 0. E to the 0 is 1, and 1 times A is A. So I'm left with 15 over 1 plus A. And then I'm back to doing the same thing I did with that logistic last time, where I was going to multiply by the denominator, move it to the other side, divide by what was there. So I'm going to divide by the 5 and subtract the 1. So A is 2. So now I know C and I know A. Last thing I got to do is figure out the K, and I'm going to use the 110 to do that. So I'm basically doing the exact same thing as I did on step 2, except that I'm using this new ordered pair. So it's going to be 10 equals 15 over 1 plus, we now know the A value is a 2, times E to the negative K, and I'm going to put in a 1 right there. Okay, let's take that denominator, let's move it to the other side. So I have a 1 plus 2 e to the negative k. That's going to be times 10 equals 15. Divide by the 10, and you get 3 halves, or 1.5. Subtract the 1. And now I'm going to take my 0.5 and divide it by 2. And then I'm going to have this term isolated. And I'm ready to switch to a logarithm, a natural logarithm. So this is the natural log of 0.25 equals my exponent. And so I'm going to type that in my calculator and then switch the sign on it, and I'm going to know my K. So the natural log of a 0.25, and then change the sign, I get 1.38. Okay, now my goal was to write the model, so here I go. I've got everything I need. I'm going to squeeze this in. All right, f of x is equal to 15 over 1 plus 2e to the negative 1.38x. And there's the model. All right, now that's some work, no doubt about it. The process, once you get the hang of it, is not all that hard. You just got to remember all your steps to it. Okay, let's talk about some of the other models. Okay, so let's do some exponential models. Now, we have some options here. We've talked about exponentials. This is kind of that basic model. This is what we've used before. Make notes as needed here. A, remember, is the initial value. B is the growth factor. Sometimes that growth factor can be written as a 1 plus R. Sometimes it's just already combined into a B value. We can also do an exponential model where the growth factor is actually written with an E value, an E, and then instead of just having an X, you put a constant up here. So this is another variation. This is still your initial value, but you're incorporating that E in that growth. Let's try using that model with the E's. Looks like here the value of an iPhone when purchased is $900. All right, that's your initial value right there. That was the initial cost. When you're ready to upgrade in 4 years, its new value is $250. Okay, write an exponential model and predict the value after 6 years. Okay, every time you do these problems in your notes on your test, you always start on the far left because I don't give you a ton of room on your notes packet. So you're going to learn to, like, you probably already have learned. Okay, so over here, what I currently know is that the initial value is 900. But then I have this e to the kt. And I don't know what K is a constant. I realize that, but I don't know what it is for iPhones. So I'm going to go ahead and plug in this right here as an ordered pair. At time 4, the value is $250. So let's type that in. 250 is equal to 900 e to the k times 4. And then we're going to solve this for k. The k is caught up there as an exponent, so I imagine I'm going to be doing a logarithm here to get it out of there. But let's start with a 250 divided by 900. And then I'm going to switch it to a natural log of the 0.278 equals my exponent. And then I'm going to come back and I'm going to divide by 4. Okay, so then the k value will equal. Now, when you're doing this in your calculator, remember, there is no rounding. Go grab that full value when you're doing your natural log, close the parenthesis, and then divide it by 4. Okay, so my k value for this iPhone is negative 0.32. I can store that or I can go grab it, whichever. Because now what I'm going to do is write the model and predict the value after 6 years. So the model is going to be this right here. Y equals 900 e to the negative 0.32 t. That's the model. Now, when I use the model to find the value after 6 years, I don't get to use this rounded number here. I will have to go grab that on my calculator. But ultimately, I'm just plugging 6 in. So I'm going to have y equals 900 e to the negative 0.32 times 6. All right, so I'm just going to type it all in as is. I got 900 times, and then I do second ln to get that e to the, and then I hit, or really I just go up and grab that k value, and then times 6, enter. All right, so what I have, this is money, so I'm going to say that the value after 6 years is $131.76. Okay, now I'm trying not to spend a ton of time on every scenario. So I'm giving you kind of one example and then moving on. Here's another type. This is a messy one. You've probably seen Newton's law of cooling. It's got a lot of stuff going on. This is measuring how quickly something might cool down. So this is your temperature at a particular time. It's usually like your ending temperature. This is T sub M. That's the surrounding medium temperature, or what we call room temperature. T sub O always is initial, surrounding medium. E is just a number. K is a constant that varies depending on what's cooling off. And then T is your time. Okay. Now, the way this will work is you always run through Newton's law of cooling twice. I'm going to give you some sort of a scenario because you got a lot of variables here to figure out. So I'm going to give you some sort of scenario. Ultimately, you got to figure out this K. I'm going to give you enough information that you can fill in everything except the K, and then you go solve for K. Once you know what the constant is for that particular substance, then you can use your new K value to answer the ultimate question. So here we go. You have a cup of coffee. It has cooled from 99 degrees to 55 degrees after 8 minutes in a room at 20 degrees Celsius. Boom. All of that info. Let's look at what we could fill in. This is your ending temperature. So that's 55. The surrounding medium is 20. The initial was 99. Surrounding medium was 20. E is just a number. I don't know what K is, but I know it happened in 8 minutes. So I have everything except for the K. So I'm going to use that first sentence to go find K. Once I know K, I'll start all over and use it to figure out how long it'll take to cool to 35 degrees. You got to keep full values, which means storing or doing a lot of going up, up, up. Now, I've given you extra space to complete this problem, so be sure to flip to the next, I think it's on the back side maybe even, but go to the next page, make sure that you're not trying to squeeze it in on that same slide. Okay, so here I go. I've already got it split up. We're going to do Newton's law of cooling twice. So for that first scenario, we knew that our ending temperature was 55. The surrounding medium was 20. This is a plus sign. Do not lose track of that, guy. So many people, I'm telling you, it happens all the time that people lose this plus sign and it starts to turn into multiplication. All right, the original was 99 minus the surrounding medium, e to the negative k, and that happened in 8 minutes. The unit of time doesn't really matter as long as you're always consistent. So I pretty much dictated, okay, I'm going to be in minutes here. Okay, so now what I'm going to do is I'm going to start peeling away to solve for that k. So let's subtract the 20. And I can go ahead and do the 99 minus 20. That's just a 79 e to the negative 8k. So now I'm going to do 35 divided by the 79. And then I'm going to switch that to a natural log of the 0.44 equals the exponent. Come back and divide by the negative 8. Okay, I'm going to type this in, but I'm going to go grab the full value on that 0.44. Divide by negative 8. Okay, so here is my K value. Now, I can just plan on going back up and grabbing that, but I'm going to refresh your memory on how to store that if that's maybe easier for you. So right now with it sitting there, you just hit store, which is left of your 1 key, and then alpha, and you can choose K if that helps you. You can just choose A because it's right there handy. I guess I'm going to do a K just so I remember it's my K. So then I just hit store, alpha, K looks like it's the left parenthesis. Press enter. And now whenever I need that number, I'm just going to hit alpha K. Here we go. We're starting all over. The question was, how long is it going to take to cool off to 35 degrees? So the scenario I had it cooling off to 55 degrees. So I want to get a little bit cooler, so it's going to take a little bit longer than 8 minutes. Let's see how much longer. It's not a linear relationship. It's an exponential decay kind of relationship. So I'm going to start back at the beginning. And the ending temperature, though, this time is going to be a 35. The surrounding medium is still 20. The initial was still 99. minus the 20 e to the negative. Now I know this number, negative 0.101. It's really 102, I guess, actually, but it doesn't really matter because I'm going to use the full value anyway. And what I'm solving for is t. Okay, now you really truly are doing the exact same thing we did on the left here. It's just you're finding t instead of k. I'm going to have you pause the video to finish it on your own and then come back and make sure that you agree with me before we keep going. Okay, I used full values on everything and got a 16.33 minutes. If I wanted to know that in minutes and seconds, remember that I would just subtract the 16 off of my answer so that I just had the decimal part, and then I would take that decimal part times 60 to turn it into seconds. All right, I have one more application for you. This one's going to be a logarithm example. And it looks like a lot of info here, and it is. We've got a Richter scale here, and this is how they determine how intense, well, really, they have equipment that tells you how intense an earthquake is. They use a seismograph to find that, but then they assign it a certain Richter number. And so this is kind of the Richter scale numbers, and then here's kind of what happens. So here's how this works. So we're going to compare earthquakes, ultimately is what we want to do. This is how the formula they use to come up with that Richter scale number. The Richter scale number is the logarithm of the intensity or the strength of the earthquake divided by 0.001. And the intensity we will have to give you because it's measured by the seismograph. Okay, so here's what we're trying to do today. I'm going to give you two different Richter values, and you got to figure out how much greater in intensity one earthquake is as compared to the other. So I give you one that has a Richter scale at 2. That's not very intense. But then we have one that has a Richter value of 8. And how much more intense is this one than this one here? Now, it's not 4 times as intense. It's not linear. So be careful with that thinking. So now I'm not going to do that particular one. I'm going to actually do some real earthquakes. So I've got some data here that we did some Googling. Let's compare some earthquakes. All right, so the Richter scale numbers for these earthquakes, the 2011 Japan earthquake, this was a really bad earthquake. Well, but really what was bad from it was that there was a tsunami. The earthquake caused a tsunami, and then it actually hit a nuclear reactor plant, and it was pretty kind of a big deal. So it had a Richter scale value of 9. So yeah, pretty big earthquake. The latest Kansas earthquake, we do actually have earthquakes in Kansas. This varies depending on what year we're doing it, and we just Google what's the latest one. You'd be surprised. We have them all the time. Like probably had one yesterday, but we came up with a 3.1 was the one we checked and found. Okay, so now what we're going to do is we're going to compare how much more intense was the Japan earthquake compared to our Kansas earthquake. So what we're going to do is we're going to set up these two equations for the first one and the second one. And then we're going to compare their intensities. So the intensities are the X values. So I'm going to always have the stronger one be on top. So I guess I'm going to have that be Japan. Let this, I don't know, that really matters which one's X2 and X1, but have your stronger one on top compared to your weaker one. So I'm going to set up this formula, and the Richter scale number is 9 equals the log of, I don't know what its intensity is, over 0.001. So the first thing I got to do is switch this to an exponential. So it's a base 10, it's common log. So a 10 to the 9th is equal to x over 0.001 multiplied by the 0.001 and we're going to have that value. So let me see what that is. 10 to the 9th times 0.001. All right. So the intensity of this was 1 million. Okay, let's try the Kansas one. So the Richter scale number was 3.1 equals the log of its intensity over 0.001. Do the same thing, switch to an exponential. And then multiply by the 0.001. And that will give us our intensity. So 10 to the 3.1 times 0.001. And I have, oh my, look at that, 1.26. So to compare the two, I'm going to take 1 million and I'm going to divide it by 1.26. Sorry, I'm just putting this in the middle. Should have scooted that one over farther. And I'm going to go ahead and keep full values on that. All right, it is 794,328.2 times stronger. The Japan one was. Okay. Let's try another one. Now we're going to compare the Japan earthquake again, which remember the Richter scale value was 9, to the Haiti earthquake in 2010. Okay, the Haiti earthquake was actually a 7 Richter scale. Look at that. That 2 nice numbers. That's going to come out nice for us. Okay. So let's see how much stronger the Japan earthquake was. But we're going to try this a little bit differently. We're going to do this a little bit more efficiently. Because here's what I'd like you to notice. If I'm going to do this first Richter scale number, and so what I did was I had the Richter scale number for the first one equals the log of the intensity over 0.001. Now think about the process in solving this. The first thing I did is I switched this to an exponential. So it's going to be a 10 to that Richter scale number equals the intensity over 0.001. And then I immediately multiplied by the 0.001. And that got me my intensity. And then I did the same thing with the other one. And then I put the stronger one on top of the weaker one. Okay, so let's pretend this first one I just did is the stronger one. So here's what I would have had. I would have had 10 to the R1 times 0.001, and I would have put it over the other one that was weaker. Now let's do some simplifying here. Wouldn't these 2.001s really not matter because I did it in both scenarios? Okay, so now all I really have is this. And every single time, since both of them use common law, they're both going to have a base 10 here. So I have 10 to an exponent over 10 to another exponent. Couldn't we just use exponent rules? What do you do with these exponents if you have the same base and we're dividing here? Don't we just subtract those? So ultimately, this ratio, how much more intense is it going to be? It's always going to be 10 of the stronger one, maybe I'll call it RS, R sub S, the stronger Richter number minus the weaker Richter number. And that is it. I mean, that's all I really have to do. I don't really have to work through this whole thing and do the logarithm. Okay, so in this case, if I was doing the Japan and Haiti earthquake, I don't have to go through it like I did on the previous one. All it really is 10 to the 9 minus 7, which I wouldn't do that next time. I'm just showing you here. Oh, okay, it's 100 times stronger. That's what that means. So Japan, I should say that Japan is 100 times stronger. Okay, let's go back to this. Remember the original question where I had a Richter scale of 2 and a Richter scale of 8? It's not, this got cut off, it's not 4 times stronger. It's, what do you think? How many more times stronger would the Richter 8 be? You should be doing 10 to the 8 minus 2 is 6, and 10 to the 6 is just 6 zeros. So it is 1,000,000 times stronger. Okay. All right. So really, truly, this is what I want you to do from here on. I don't really want you to work through it. You don't have to know the formula. If you remember what we've done here, you don't need the formula because you understand the relationship. All right, and then I'm just going to skip over the last example. It's kind of the same deal. There was actually an earthquake in, I think it was in the 80s, maybe, in LA when the World Series was going on. Okay, so here's what your homework is. You've got 10 task cards, so that means you have 10 homework problems. That's all you have, 10 problems. Oh, I lied. And there's some extra ones on the worksheet. So you should have a handout that you are working on, and I have a spot for all the different task cards. If you don't have the task cards, they are in Google Classroom. So good luck. You've got this.